Hello, Chem 1. Welcome to this week's editions of our videos for stoichiometry. This week we're going to have two different videos. One very short, that's the one we're going to do first, and then hopefully a little later on today I'll get the second one done, which will be a little bit longer. But today we're going to deal with focusing on relationships between quantities within a chemical reaction. Up until this point, everything we've done has focused on one substance at a time. Whether we're looking for the number of grams in a substance, the number of moles in a substance, the number of liters of a substance, what is the empirical formula of a substance, where we always focus on one particular substance at a time. Well, that's only half the story. The other half of the story is what to do with when you're relating different substances within some type of a reaction. And very often stoichiometry is always connected with, like, again, I'll use baking or cooking. If you're baking a cake and you require 2 cups of sugar and for every 4 eggs, but you only have 2 eggs, well, there's a ratio between 2 different materials. If I only have 2 eggs but I need 4, so I only have half the number of eggs I need, so I can only use half the number of cups of sugar in my recipe. So there's a ratio between the amounts of the two. Well, that's what we're going to be dealing with in this one, is talking about the big picture ratios between 2 substances. For homework with this one, there will be a Google Classroom. I'll create it right after I finish this video. It's called mole to mole practice, and allow you to go between moles of one substance and moles of another substance. And you just have to, again, much like some of the quizzes, you'll answer the question and see whether you got it right, and it should be fairly quick, at least for this one. The next video is going to be a little bit longer and a little bit more work involved in the homework. So, as a warm-up, just to see whether we got the juices flowing from what we've done before, if I were to ask you to predict the products and to write the balanced chemical equation for the following reaction, could you do this? This is from at least maybe 3 weeks ago, back when we were doing balancing chemical equations. So the reaction is that calcium chloride reacts with sodium phosphate in a double replacement reaction. Go ahead and pause the video for a second, try to balance that equation. We're going to be using balanced equations a lot in this video, that's why we started here. So go ahead and try that one on your own. Okay, so let's see how you did. So if you were to balance this equation of calcium chloride reacting with sodium phosphate, first thing you need to do is start with what your reactants are. You have calcium chloride. Calcium is a +2 and chloride is a -1. And then sodium phosphate. Sodium is a +1 and phosphate is a -2. You do your crisscross and get your compounds. Then you have to figure out what your products are. Well, since it's a double replacement reaction, the sodium and the calcium, the 2 cations, are going to switch places. So you're going to get calcium is now going to be paired up with a phosphate, and sodium is going to be paired up with a chlorine. So calcium still being a +2 and phosphate being a -3, so you have to do the crisscross of taking the 3 down and taking the 2 down. And then sodium being +1 and chloride being -1, that worked out just fine. So I've written my products correctly, and then finally I have to do my tallies and to figure out what my numbers, my coefficients are for each. And I got that I needed 3 calcium chlorides, 2 sodium phosphates, and when those react together, I make 1 calcium phosphate and 6 sodium chlorides. Did you get that same answer? I hope you did. So if this is your balanced equation with the 3s, the 2s, the 1s, and the 6s, my question for you that revolves around this video is, what is up with the coefficients? What do they represent? What do the coefficients in the balanced chemical equation represent? Well, they should, if you think about it, they represent that for every 3, I'll use the 3 up front, for every 3 moles of calcium chloride, I need for every 3 atoms or molecules of calcium chloride, I need 2 molecules of sodium phosphate. So what it does is it represents a ratio of particles, or a ratio of the actual molecules. So that since particles and moles have a constant ratio of 6.022 times 10 to the 23rd particles per mole, it also represents a mole to mole ratio. And under extreme circumstances, those extreme circumstances are when the temperature is constant and the pressure is constant, and we're talking about gases. then it also represents a volume to volume ratio. So what we have here is the ability to go between one component in a chemical equation and compare the number of particles that are needed for that one, and to see how many particles of something else we need, or mole to mole, or volume to volume. Let me show you what I mean. So what we've done is we've used the BCE, that's the balanced chemical equation, to connect volume of one substance to volume of another, or moles of one substance to moles of another, or particles of one substance to particles of another. We're to look, again, the key here is for today and this week is we're going to compare amounts of different materials that are connected via a balanced chemical equation. So for example, if I had octane, C8H18, and I wanted to know how many moles of oxygen, O2, are needed to react with 1.6 moles of octane, well, I'm comparing two different substances in this balanced chemical equation. I have a 2 to 25 ratio. Okay, I'm starting off with 1.6 moles of octane. I know that, again, using dimensional analysis, we talked about this a lot for the last few weeks. It's all about dimensional analysis and how to incorporate dimensional analysis. If I have a 2 moles of oxygen for every, 25 moles of oxygen for every 2 moles of octane, and I want to make sure my moles of octane cancel, I'm going to put my conversion factor in this orientation, 25 moles on top, 2 moles on the bottom, and then do my math, and I get that I have 20 moles. So what this says is, if I want to react, if I have at my disposal 1.6 moles of octane to react, it's going to take 20 moles of oxygen to completely react with that octane. It's a ratio of moles, and that's what this conversion factor is in the middle. You can do this from mole to mole. You can do this for volume to volume. You can do, as long as the two materials are both gases and they're both at the same temperature and pressure, or you can do this for particles. Here's one with volume. How many liters of nitrogen are needed to react with 3.25 liters of hydrogen? Again, here's the caveat. If both gases, they both have to be gases, are collected at 25 in 1 atmosphere, they have to be at the same temperature and pressure. If you change the temperature, say it's hotter in the beginning than in the end, or if it's collected at a different pressure in the beginning and the end, this conversion factor, this process doesn't work. We'll cover that in Chem 2 as to what to do when you're not at the same temperature and pressure. But in this situation, what you would do is start with your given, like you always do, 3.25 liters of hydrogen. You would use your conversion factor. In this case, they're asking about nitrogen as it relates to hydrogen. They're both on the left-hand side. And I want to make a point before I do this, to anything else. They don't have to both be on the same side. The two substances you're dealing with don't have to both be on the same side of the reaction yield side. They can be one on one side, one on the other. They can be both reactants, both on the left side. They can be both on the right side, but it always compares two materials in a balanced chemical equation. Both the examples that I've used here both happen to use two reactants. So it's a 3 to 1 ratio, 3 for the hydrogen, 1 for the nitrogen. Do the math, round to sig figs, and I get 1.08 liters of nitrogen is necessary. Okay, now, with that being said, mentioning sig figs, these coefficients that are associated with the conversion factor for mole to mole or volume to volume, those are absolute numbers. You're not talking about in a balanced chemical equation somewhere near 1 mole will react with somewhere near 3 moles. It's exactly 1 atom will react with exactly 3 atoms, or in this case, exactly 1 mole will react with exactly 3 moles. And when we said earlier, when we're talking about sig figs, exact numbers don't count in your sig fig calculation. So this has 3. This visually appears to have 1, but they both have an infinite or number of sig figs, so they're exact. So we ignore them. So our final answer can have 3. Okay, so that's basically the first lesson for the week, where we're talking about mole to mole ratios. What's next? Well, what we're going to do at the next video is we're going to look at what happens when we have more measurable quantities. Because let's be honest, mole is a concept that allows us to take measurable quantities like volume or grams or I guess, other aspects, but we'll focus mostly on volume and grams, and compare measurable quantities of the two. So we're going to compare masses and volumes and use the balance equation. And I'm going to introduce in the next video something called the explicit method. So if you got anything out of this video, go ahead and hit the like button. Go ahead and you can leave a comment as long as it's school appropriate. And subscribe if you haven't already. I'm up to like 140 subscribers, so that'd be fantastic to bump it up, get closer and closer to that 200 range. I will see you on the next one. Stay safe, stay happy, healthy, and practice that social distancing associated with these times we're in right now. Toodles.